Hello everyone, I'm Lorenzo Tunesi. I'm a third-year PhD student at Politecnico di Torino, and today I will be presenting to you my work on silicon photonic switching for elastic transparent optical networks. I will start with a brief introduction about myself. I got my bachelor and master degree in electronic engineering at Politecnico di Torino, and during the course of my PhD program, I was author in 5 journal papers, 40 conference papers, and 1 patent proposal, which is currently in the disclosure phase. My main avenue of research is silicon photonics for optical communication, but in general, photonic integrated circuits are becoming a key enabling technology in a wide variety of fields, such as biomedical, quantum, and computing. This is due to their many advantages with respect to the electronic counterparts, such as higher speed and bandwidth, lower thermal effect, and higher power efficiency. The choice of silicon photonics as a technological platform is due to its flexibility. It is compatible with traditional electronic CMOS manufacturing, therefore it is cost-effective and can be scaled up for mass production, while still allowing integration of complex multifunctional photonic chips. This is ideal for the optical communication landscape. We're seeing a rapid increase in traffic and we are expecting an exponential increase in the coming year. Therefore, the non-integrated traditional solution cannot scale up anymore to meet the demand. Silicon photonics can not only handle the requirements, but are shaping up to be the future technology that can handle and can be the backbone for the expansion and improvement of the optical networking landscape. Therefore, the goal of my PhD has been the design of novel devices that can handle this modern communication standard and the development of a generalized design strategy to connect the more physics-based material and device field with the higher abstraction of the telecommunication and networking field. This is done through a vertical approach, deploying different model and different techniques depending on the problem at hand. These range from physics-based numerical simulation for the device up to circuit block analysis for the transmission and networking scenarios where we have larger chip. And so this leads to a fast and efficient simulation pipeline that can handle both parts of the spectrum without losing any accuracy and without glossing over the complexity of the physics behind wave propagation in the device. Three main results can be highlighted of the study done throughout the PhD program that showcase the layer awareness that is needed for this kind of work and the advantages of using a bottom-up approach. So I will start with a device analysis of a programmable multi-channel switch. The issue at hand was that flexible bandwidth for elastic networking is not available in traditional devices, and so we need to add some innovation either in the technology or in the material to expand the capability of PICs. I opted to use phase change material, which are material whose crystalline structure can be controlled through the use of a thermal or optical signal, and this leads to a non-volatile modulation of the optical properties. This material, applied to the traditional waveguide structure of, in this case, a grating-assisted contradirectional coupler, lead to a really novel device, which is power efficient, flexible, fully integrated, and programmable, and allows a multi-channel shaping of the spectrum. And this is quite novel, and so it has been patented, and it's currently under the disclosure phase. Moving towards a larger circuit and higher in the telecom sector, we can move to multi-stage switching network. In this, we've analyzed the Benesch switching topology, which is a traditional structure used both in photonics and electronic switching system. To this end, and to analyze this problem, I developed a design suite that automates the testing and comparison of different device implementation, control strategy, and network sizes throughout this kind of large-scale switching matrix. And thanks to the data extracted from this, we developed a machine learning agent which can estimate the transmission impairment and the optical routing even in large-scale devices, reducing the penalty margin that the network operator can and must consider, and therefore optimizing the network and allowing higher capacity. Moving towards the union of the two, so novel devices and large-scale telecom application, we move towards wavelength-selective switches. The issue here is that we need multi-band WSS able to route different channels in really large spectral windows. And so to this end, I designed a novel modular multi-band WSS architecture operating in the SC plus L scenario, and I developed a straightforward penalty prediction scheme to abstract this device for arbitrary size and for application in networking scenario. And the study of the component has been abstracted from the waveguide, and so the silicon layer, up to the networking, allowing the extraction and characterization of the penalty. So in conclusion, I think I've shown that silicon photonics is an integrated platform which holds promising properties for the next generation of optical communication, and my main contribution have been the development of highly reconfigurable devices, the bottom-up design and penalty evaluation in multi-stage network, analysis and optimization of different devices and design for optical telecom application, and the development even of novel architecture for WSS. So thank you very much for your attention.